Adding the @transactional annotation to a Java method is supposed to guarantee database safety, but relying entirely on it can silently corrupt a database. Imagine a standard payment flow. You have a primary method designed to save a user's account to the database, and it calls a secondary method to process their credit card. You explicitly tag both methods for transaction management. During execution, the payment processing fails and throws a runtime exception. The expected behavior is an immediate rollback. Instead, the user account data commits permanently to the database, leaving the system in an inconsistent state. The developer placed the annotation correctly, the code threw the correct exception, yet the system completely ignored the rollback protocol. The Spring framework didn't malfunction here. The failure happened because the developer misunderstood the mechanical realities of how the framework actually executes code, creating a phantom state of data corruption. To understand the failure, we have to look at aspect-oriented programming, or AOP. Spring uses AOP to separate transaction logic from your core business logic using an invisible wrapper called a proxy. When Spring sees the @transactional annotation, it instantly encases your target object inside an outer boundary called the proxy. Incoming data strikes this proxy first. It mechanically opens a transaction, then passes execution to your code. Exiting data hits the proxy again, closing the transaction. The proxy operates as a literal gatekeeper. If a process does not cross that proxy threshold, the transaction manager remains completely blind to it. Now let's apply that gatekeeper logic to our failed scenario, where the user-saving method called the payment processing method. In this diagram, the first method inside the target object calls a second method inside that exact same object. Originating internally, it routes directly to the destination, completely bypassing the proxy boundary. The second method triggers an error, but the outer proxy boundary remains entirely inactive. Spring ignored the rollback command for a simple reason. It had no mechanical awareness the secondary method was ever executed, let alone that it failed. This is known as the self-invocation bypass. It proves that writing declarative code provides a dangerous illusion of safety if you ignore the physical boundaries of your objects. Restoring the transaction protections requires explicitly fixing that proxy bypass. This diagram shows the first and cleanest architectural option, separating the beans. By moving the secondary method to an entirely different Spring service, the internal call becomes an external call. The data routes out of the first proxy and successfully strikes the second. A second option is self-injection. You instruct a service to auto-wire a reference to itself. By calling the injected reference instead of the local method, you force the internal call to route outward and hit its own proxy. A third approach is to abandon proxies altogether. This diagram illustrates AspectJ compile time weaving. Here, the transaction logic is injected directly into the core bytecode of the target object, removing the outer proxy boundary completely. As the visual shows, the target object now safely processes the internal self-invocation and triggers the transaction natively. However, while AspectJ solves the issue at the source, it adds significant complexity to the project's build process. Solving the proxy bypass always requires forcing the system to recognize your transaction boundaries. You either change your architecture to respect the proxy, or you change your compiler to remove the proxy. But fixing self-invocation will not eliminate all silent transaction failures. There is a visibility trap. Mechanically, Spring's proxies cannot override private methods. If you place a transactional annotation on a private method, the framework silently ignores it, offering zero runtime warnings. There's also a strict rule for exceptions. As this split-screen graphic shows, Spring's default behavior only triggers a rollback for unchecked runtime exceptions. A checked exception, like an I/O error reading a file, triggers a full database commit. In the early days of enterprise Java, developers manually opened and closed database connections. That manual process offered absolute transparency, which modern frameworks now obscure behind layers of abstraction. Relying on abstract declarative annotations without understanding their precise mechanical limitations transforms a developer convenience into a critical system.